Okay, we have another related rate problem, and this time the diagram is more important than ever. You have to be very, very careful with how you set this up. So this says that a 6 foot tall person, so here I'll put a stick person I'll say is 6 foot, is walking away from a 20 foot, so they're on the ground, so 20 foot lamppost at a rate of, so this person right here is going that direction at a rate of 3 feet per second. All right. Assume the scenario can be modeled with the right triangle. So what they're saying is something like this. You draw that through there. Now look at what we have. We have this triangle, and inside that triangle, which they share two things. They share this angle. They both have a 90-degree angle. So now you've got a similar triangle situation, and you can set things up as a ratio. At what rate is the length of the person's shadow changing when? So this length right here is 13 feet. I'm going to call that X, and we don't know this, but I'm going to call that Y, and that rate is dy dt, and they're walking away. That person's walking away at 3 feet per second. So that's the diagram I have here. Have somebody kind of more jogging away. Here is the lamppost, 20 feet, 6 feet. So notice this big triangle has this ratio. This length right here is X plus Y. That length in ratio to its height is X plus Y over 20. And then we're going to compare this length, which is Y, over this height, which is 6. So see what we did there? So instead of having a specific formula, we have a ratio situation. So that's what I mean. It's not always a specific formula, but if you're really careful about how you set things up, then things kind of write themselves. So let's get going. What we know is the person is walking away at a rate of 3 feet per second. Whoops. And the diagram is right here. It's very much smaller, so you can't really see it very well. But this length we call X, this length we call Y, and when we go to solve, at the given moment when this length is 13 feet, okay, so we're going to set that formula up. It's just going to be a ratio. So this length, X plus Y, is to this height, as this length is to this height. All right? And then what we need to find is let's see, at what rate is the length of the person's shadow changing? Let's see. Oh, I apologize. I explained this kind of strangely. We do want to find the dy dt, but that obviously is the person's shadow. It's the lamppost shadow that is the dx dt. So it's right here, right? And it's changing at 3 feet per second. So I did not word that very well, but now we have the setup. So now we're going to set up that ratio. X plus Y over 20 is equal to Y over 6. And then I'm just going to cross multiply. And remember, it's because we can multiply. If I multiply both sides by 20 and both sides by 6, on each side the 20 and the 6 cancel. 6 times X is 6X, 6 times Y is 6Y, Y times 20 is 20Y, and then I'm going to subtract. I'm going to get the Y's to one side and the 6X. Now we can go ahead and take the derivative of this non-function. Okay, so because we are given a dx dt and we have to find, you actually have to tack on a dx dt here as well as a dy dt. So that's what we did. I said the derivative of 6x is 6, tack on dx dt. The derivative of 14y is 14 dy dt. Well, we know what dx dt is. Dx dt is 3 feet per second. And then we're going to divide both sides by 14. And what we have left is 18. 6 times 3 feet is 18 feet over 14 seconds. But that can be simplified because they both have a 2 in common. So the person's shadow, it's changing at a rate of 9/7 feet per second is what we found. And that's it for this one.